Well, hi, and here we are. I'm hoping that I can give you a bit of a lead in on some of the trig functions, particularly sine and cosine graphs in this video, that perhaps you can watch this before you come into one of my lessons, and it might help you moving forward. So the first thing I'm going to do is just have a general play and maybe even remind you of a couple of things on Desmos. You'll see how I've opened a Desmos page that I'm recording. I'm just going to remind you of a couple of things. Firstly, if you want to sketch a sine or a cosine graph, you just need to type in sine y equals sine x, and it pops up there. So if you open up the keyboard here, you'll notice it is an available function, but really that's it's quite fiddly and probably not worth doing. So just sine x and on you go. I'll close that. So here's my y equals sine x, and you'll notice some features already. It looks a bit like what we would call a wave function. And it's used to model lots of wave movement in physics, so on and so forth. And so it actually has this really deeply ingrained repetition. If I slide along, it just keeps on going the same way. Okay, but you will notice that the function I've got sketched has these x-intercepts, but they're not nice numbers. They're actually irrational numbers because they're measured in radians. So if I keep on zooming in, it'll never really hit a nice point. Those x-intercepts, or really any of the points, like for example the peaks, which I might have zoomed in a bit too far to find, but the peaks of the function here will also not have nice points. So you can see there's a peak of my function. I'll probably suggest that while we're playing along with this, that you could have your computer open, have Desmos up as well, and just be playing with it. I'm going to change some of my settings very quickly. So you're seeing here I can add arrows, etc., axes label, minor grid axes. Now the reason is I've got it in radians, and so you'll know now that when we are using radians, if we're also using trig functions, then radians become a really important feature of what we're doing. And so what I'm going to do is I'm going to change my x-axis. Instead of going from what it is now, because I zoomed and moved, I'm going to change it to be a radian measure. So I'm going to have it go from -2. Now I want it to go from -2 pi, and to get the pi symbol, I don't go to my calculator again, I just type pi, and there's the pi symbol. Just another little shortcut for you. And I'm going to make it go up to 2 pi. Now I know a bit about this stuff, so I know why I've chosen those. I'm also going to change the step. So I want it to be going up in pi over 6s. And from your work in exact values, you'll know that pi over 6 is our lowest denominator of some really important angles. So I'm going to go with pi over 6. I also know a bit about these functions, and I know that if I have my y-axis go from, say, -1.5 up to 1.5, it gives me a bit of room above and below. This will give me a really good view of the sine graph. So there it is, zoomed in there. Now it's going up in pi on 3, so Desmos has overruled me a little bit. And you'll notice here pi on 6 is half of pi on 3, so it's just there. And pi on 2 is in between pi on 3 and 2 pi on 3, so it's just there. Pi on 2, well, you'll remember that pi is 180 degrees. Pi on 2 is 90 degrees. Pi on 3 is 60. 2 pi on 3 is 120, and you can work out the rest from there. If this is 180 degrees, then each of these lines is worth 20 degrees as we move up. Now, here's some interesting things. First of all, our sine graph peaks at 1 and troughs at -1. So you're going to see that language. I'm going to write it on my OneNote in a minute for you to have a look at and write down if you want to. Peak at 1, trough at -1. That's a minimum and maximum value. And it's the same everywhere. There's a peak over there. Here's a trough. Always goes from 1 to -1 while it's the plain sine function. We can do some stuff to it later on to make it not do that, but just the plain one, that's what happens. Now if I just scroll to the side here a little bit, you'll see that it starts at 0 and then gradually moves up until it's slowing down now. It's curving down, 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 and it reaches its peak. Then it comes back down, and it sort of does that top half from 0 to pi, and then it does the bottom half, and it gets to 2 pi, and then it repeats itself. So the sine function, the standard sine function, repeats every 2 pi. And that's really interesting, because it's also the value that we use when we were doing some unit circle work earlier. And you'll note also that this is 360 degrees, which is one full rotation of a circle. So a sine function does some stuff every 360 degrees and then starts again. It's got that really direct repetition. So 0 to 2 pi is our repetition factor there. Now we talked a bit about sine. Now I want to talk quickly about cos. Very, very similar. So again, I just type in cos. There it is. And in fact, let's put sine back up here. Y equals sine x. You can see cos is basically sine x. It's just been shifted back pi on 2 radians. So that's 90 degrees. It's just out of phase by 90 degrees. So cos, instead of starting at a central point, moving up, cos starts at a peak and then starts to move down. But you'll see some really beautiful symmetry here. So while sine, the blue one, has this really nice 180 degree rotational symmetry, if you rotated it around this point here in the center, it will, so the origin, it will give you this the same thing after 180 degrees. Cos has a reflective property over the y-axis. So if you reflect over this line, x equals 0, then this point will move to this point over here, and you'll get that reflective property. So there's some really important features of cos and sine. Just some general musings. So I haven't put them down yet. I'm going to write a few things down now. I've actually pre-prepared some. And I'm wondering if maybe I've added a few too many grid lines, but I hope you can just ignore those. Some of them will be important, and I just wanted to be able to pick them out if I needed to. The scale's the same, but I've gone from negative 2 pi to 4 pi this time. So here are some important points. That point there is called a peak. And there's another one here, and there's another one over there. And this point here is called a trough. And there's another one here, and there's another one here. So you've got peaks and troughs. They're also, they're the maximums of the function and the minimums of the function, which might come in handy to use that language. And we've also got this special feature. So this x-axis, in this particular case, the x-axis is equal to what we call the midline. I've also heard it called the center of equilibrium. But you know what, midline is shorter and mathematicians are lazy, so we'll probably go with the midline. It's the center of our motion. And the sine curve starts at a midline and heads upwards. That's where sine starts. So we've got our midline, and in amongst and related to that midline and the peak, we have this value here. That thing there is called the amplitude. And you'll hear that language used a lot in physics in the context that we use waves for in physics. So the amplitude is really important. And the amplitude between the midline and the peak is exactly the same as between the midline and the trough. So this is also the amplitude. Now the other thing that we do have is something called a phase shift. And our phase shift is the movement horizontally from the y-axis. So that phase shift. Now this is a sine function. It's a standard sine function. So it's starting where we expect it to start. And that means it has a phase shift of 0. But if we were trying to model this with a cos function, remember the cos function starts at a peak. And so whilst I have actually modeled a sine function here, if this was a cos function, it would have a phase shift of plus pi on 2. That's for cos. So there's a couple of language pieces for you. There is one more that I just want to bring up, and this one's really important, and so will come up a lot. But I'm just going to do it down here. This is where I have the space. That distance there is called my period. And so you'll see that it's a really important feature as well. Now the period is the distance between two troughs, or it's the distance between two peaks. We've got this really nice symmetrical consistent wave model here. So it will be the same. That should be the same distance. That's also the period. Or it's the distance between two center of equilibriums as long as they're going in the same direction. So see that one's going down, that one's going down. So the center of equilibrium can be a bit more confusing because there's twice as many. But the two center of equilibriums going down, that's our period. And in this case, you'll see that from this center of equilibrium going up to this center of equilibrium going up, it takes a period of 2 pi to repeat for this particular model. 2 pi being that full rotation around a circle. So that's what we expect. So there it is. That is our standard sine function. And we've also looked at our standard cosine function and some of the important language associated to them. So definitely worth having a watch through this video again, noting down this language and making sure you're associating it with the right components. And of course, always bring your questions. All the best.